Good morning.
Yeah, good morning. So good evening to you. I think let's wait for another couple of minutes to start.
Yeah.
Good evening, sir. Good morning, ma'am.
Hi, Sunil.
Hi, sir.
Good morning.
Hi, good morning, sir.
Good morning.
Hello. Tiva, you're home today.
Yeah, you're right.
Well, your first name, your name changed, right? Julia.
Through my wife's Gmail ID.
Yeah. How is she doing?
Strangely, I'm not able to log in through my Gmail ID.
Okay, I guess we can start.
All right. Before I just share my screen a second. All right. So, looking at the schedule, let me try to summarize what we're going to do today. So first, I will talk a little bit about the hierarchy of matrix positivity classes. They're all very closely related to the linear complementarity problem, and I will mention a few key things. But they're not exclusively all the classes. They're not all the classes. If you look at collections of matrix classes for the LCP, you'll see more, but they're all very, very closely related. At the very end today, it looks like Deepa is going to focus more on matrix classes with the LCP. Then, after I talk a little bit about this hierarchy, I'll focus on a very specific class that, in some sense, as you will see, it sits on top of all the positivity classes. It's the weakest, in some sense, assumption of positivity. And then we'll continue with these special classes tomorrow and on Wednesday when I'll talk more about P matrices and semi-monotone matrices with a little break in between. Then on my kind of like the tutorial, the third session today, I think I will go back, unless we find something better to do, I think I will go back to some of the things I was talking about today on the principal pivot transform and mention a couple of worthwhile points of view and applications of the principal pivot transform. All right, so let's begin. hierarchy of positivity classes. Okay. By the way, at some point, definitely by Wednesday, I will ask the help of Annie Deepa to kind of like send her some files and get posted for your perusal if you so feel like, the notes and other stuff. So let me underline positivity here because as you will see, almost every matrix class that I'll mention includes the word positive one way or another. So what's the purpose of that? When you kind of like describe a tree of relationships between the various classes, you serve the purpose of better understanding these classes, right? Because their interdependencies get exposed, and you can also, by studying them individually, you work towards a unification theory and also understanding what properties cause, what properties describe the classes and what are the minimal requirements to have these properties. So it's a hierarchical, it's a unification. That's how I view it, unification effort. And, a way to understand better these classes. So let me very quickly, I'll use some notation that's it's not the best notation in the world. It's not going to mean very much except locally in this session and when we discuss semi-positive PD and semi-monotone matrices. But I'll go through it nevertheless. It's the notation we used in my book that I will mention at the very end on positivity classes. So here are the main classes I want to talk about. First one is the class SP. Okay, so this will be the so-called semi-positive matrices. Okay, what is their definition? The definition is that there exists a non-negative vector x such that a times x is positive. Okay, so A maps a non-negative vector to a positive vector. Of course, that non-negative vector is non-zero, right? Because otherwise A times x would be zero. So maps something in the non-negative orthant into the interior of the non-negative orthant. We'll study them in pretty good detail and see consequences and relations to LCT and so on in the next lecture. Another infamous matrix classes are the P matrices. These are matrices for which the principal minors of the matrix, in other words, the determinants of the principal submatrices A of alpha are positive, all of them. So for every alpha, a subset of 1, 2, down to n. Okay? So all the principal minors are positive. Now, another famous class, I will call it here locally PD for positive definite. Positive definite matrices. Of course, this built in here that they are symmetric, okay, and or Hermitian if you want, and actually, why not I use Hermitian, and x star AX is positive for all x that are different than 0 in Cn. For all vectors, x star AX is 0. We know that this is equivalent, for example, to just being, if it's real, being symmetric, if it's non-real, being self-conjugate, and then being at the same time a P matrix. So these are classical results. I won't be able to review all of them. Another good class are the doubly non-negative matrices. You won't be required to memorize all of them. We'll just work with a few. So what are these? These are doubly non-negative matrices. There are matrices A that are positive definite. Okay, they're positive definite, and they're non-negative. So they're non-negative positive definite matrices. We will refer to them as doubly non-negative. Then we have CP. CP stands for completely positive. There's so many versions of positivity that we've almost run out of terms to describe them. So what are they? So they're matrices of the type A equals B times B transpose. So they are symmetric. In fact, I wouldn't call it, they're symmetric if B was square, but more generally is just B transpose, where B is non-negative. Okay, and in fact, you may be able to write a completely positive matrix as the product of a non-negative matrix times its transpose in many ways. If B is in fact n by k, non-negative, and the k is minimal, it's the smallest k for which there exists a non-negative matrix n times k, such that A equals B transpose, then this k, this minimal k, is called k minimal is called the CP rank. You may have heard of this as the CP rank of the completely positive matrix A. Then we have the TP, which stands for totally positive matrices. What does this mean? It means that every minor, not only the principal ones, so all submatrices, all square submatrices have positive determinant. Let me write it mathematically. If you have alpha and beta, and they're subsets of 1, 2, up to n, and if the cardinality of alpha is equal to the cardinality of beta, then the determinant of A alpha beta is positive. In particular, if you take alpha and beta to be singletons, just one member of 1 up to n, then that shows that in particular such a matrix A is greater or equal than 0, right? Because these 1 by 1 square submatrices have positive determinant means, positive determinant means they are positive. So therefore, there's a weaker notion for most of these classes, weakly semi-positive, these matrices, positive semi-definite matrices. I won't tire us with all these weaker versions, but you can imagine how they work. So there is something called totally non-negative matrices, which allows these minors to be greater or equal. Another class, it's H plus. Yes.
Excuse me. I think someone has in some queries. Bharat.
Go ahead.
Yes, ma'am. Hello, sir.
Yeah.
Sir, you are considering positive definite matrix is a Hermitian. So, in this, that mean here and doubly non-negative matrix is also a positive definite. So here we are considering doubly non-negative matrix must be a symmetric if it is real.
If it is so let me see if I understood your question. I define positive definite matrices unnecessarily as perhaps complex matrices. The requirement is that they are A is equal to A star. Okay. If it was real, that would be equivalent to A equals to A transpose.
So here we are considering real those matrices which are Hermitian, like it should be there.
I did not understand your question. So they are positive definite matrices are Hermitian matrices for which the quadratic form x star ax is positive for all x in Cn.
Okay.
For all complex vectors x.
Okay. Thank you.
Yeah. All right, so let's go back to this H class. These are H matrices. And I will help, I guess, to define that with positive diagonal entries. I will indirectly define an H matrix. H matrix means something that, a lot of people will define it in different ways, but I'll define it in a way that's the most economical way, in my opinion, to define them right now. It means that there exists a diagonal matrix D with non-negative okay, I'll put here non-negative. In fact, it will have to be positive, such that A times D. So if you scale the columns of this matrix by post multiplying by diagonal matrix D, this is strictly diagonally dominant. So there are many other ways, and I think especially where Professor Sivakumar is going to talk about M matrices at some point, they're closely related to an M matrix. For example, if you take an M matrix and you find its companion, its comparison matrix, where you find absolute values and sign the entries, we get a non-singular M matrix if it's H plus. So he will make that connection. I'm not being very precise right now. But nevertheless, it's a class that contains, for example, the non-singular M matrices, which I'm going to define next. So the class M, these are the M matrices. These are matrices of the type A equals S times I minus B. Okay, I is the identity matrix, B is non-negative, square matrices, B is non-negative, and S is greater than or equal to the spectral radius of B. Okay? So in particular, that means that that A is it has a very specific sign pattern. The off-diagonal entries are all less than or equal than 0, and the this matrix has all of its eigenvalues in the right half plane, right? Because you've shifted the eigenvalues of minus b by something that's at least as big as the spectral radius, so you've moved all the eigenvalues of minus b to the right half plane. So these are very well-known, a very well-known class of matrices, and I think they will be discussed in detail later session. All right, going on for a few more. I'm going to take the class SC now. These are the strictly copositive. Matrices. What are they? Well, they are matrices which are real, symmetric. So let me make sure that I make them real. So they are symmetric, and X transpose AX is greater or equal than 0 for every X greater or equal than 0. So they kind of look like positive semi-definite matrices. And I want strictly copositive, so I'm going to put here greater than 0, and I'm going to add here different than 0. So yeah, this is a class that's very closely related to the completely positive matrices in a non-obvious way, but they're kind of like they form a dual code. All right. Let me see, I need a little bit more space, so I'll move to another page. Semi-positive, B matrices, positive definite. I'll change the thing a little bit. Doubly non-negative matrices, completely positive matrices, totally positive matrices, H plus matrices, M matrices. I think I will need, let me just check something in order for my next step to make sense. I'm going to make these non-singular M matrices, and I'm going to make this S strictly greater than rho of B. Okay, strictly copositive. All right, a couple more, and then I'll draw a picture. What are the other two classes I want to mention? I'm going to call them mon for monotone. These are the monotone matrices. And here's what they satisfy. They satisfy that they're real matrices, but if A times X is greater or equal than 0, so if A maps a vector X, a real vector X in the non-negative ortho, that means that that vector was already non-negative. Okay? So I think that's cute because, I mean, I always wondered, why do we call them monotone? Well, I guess we can guess a little bit. But let me parenthetically mention that if A times X is equal to 0 and A is monotone, right? Then, of course, A times minus X is also equal to 0. So that therefore implies that X is not negative, but it also implies that minus X is not negative, right? Because A minus X is also equal to 0, of course. So in other words, it implies that X is 0. So for a monotone matrix, AX equals 0 implies that X is equal to 0. So for a square matrix like that, that implies, therefore, that thus A is invertible. right? That's what a monotone matrix would have to satisfy. And in fact,
Michael,
yeah,
you're taking A to be square
yeah, it's square, yeah.
because this can be defined for rectangular matrices also.
Right now, I'm defining it for square. Thank you. So yeah, so then it's invertible, and then in fact A inverse is greater or equal than 0, and so I mean what I'm trying to explain is why they're called monotone. So if AU is greater or equal than AV, that implies that U is greater or equal than V, right? So that's kind of like the monotonicity we are familiar with. So anyhow, they're called monotone matrices. And I will add now one class that I will discuss explicitly another day. And I'm using an acronym or a notation for it that doesn't come from non-negative matrix theory. It comes mostly from the LCP because this is a class of matrices that is commonly encountered in LCP type of problems. This will be the strictly semi-monotone. Simply semi-monotone matrices. Real again. Okay, perhaps I should have stuck as a blanket assumption that I'm talking about real square matrices in this hierarchy, and not confuse you with the complex matrices. But what do they satisfy? They satisfy that if you take an x that's non-zero and it's greater or equal than 0, so it's a negative non-zero vector. So for every such x, pardon my informality here, there exists a k in 1 up to n such that xk is positive because it's, you can find such a k because x is a non-zero vector, and the kth component, the kth entry of a times x is also positive. Okay? So every time it hits a non-zero non-negative vector, it retains the sign of one of the positive entries, at least one of the positive entries of x. So if there's a k such that xk is 0 and a times xk is positive and a times xk is positive. All right, so let me now try to squeeze in this last in the bottom of this page. I think I can fit it all in. A schematic that summarizes the relations, summary of relations among these classes. Okay. So it turns out that SP, the semi-positive matrices, contain the strictly semi-monotone matrices, which contain the P matrices, which contain the positive definite matrices, which contain the doubly non-negative matrices, which contain the completely positive matrices. There's no way you can find relations among all these classes, so I think this is kind of a useful table we're going to create. let's fit in there the totally positive matrices. The totally positive matrices, I'll write them here. They are contained in the P matrices, and therefore they're contained in the quickly semi-monotone, and therefore they're contained in the semi-positive. But they're not necessarily contained in the positive definite. There's no relation between them, between the totally positive, the positive definite, the W non-negative, and the completely positive. So I started a new containment underneath. They don't contain any of the other classes that we've discussed so far. Same thing with the,
monotone matrices will be contained in SP.
yes, I'm not done yet. So you'll see, we will, this table will eventually envelop everything. You're right. So the Hermitian matrices with positive, it's kind of a clever table. It's not my invention, but we'll see in the end everything will be there. So the H plus matrices, I write it here, they're contained in the P, they're contained in the E and the SP, so I write them there, and they contain the M matrix. There are no singular M matrices. Now let's move to the strictly copositive matrices. It turns out that the strictly copositive matrices are semi-positive. So I'll write them here. Okay? Oops, not SP. Let's see, strictly copositive. And they contain the positive definite. Just a second. Hold on in a second. I think I missed a class. Let me just go back, because now here there's a class. Did I miss a class? Yeah, I missed the easiest class of all. I'll write it down and I'll go back and add it up there. So there's this class EP, which if you think about it is kind of like the best class of all. This means entry-wide positive, right? So we'll run out of acronyms. So, and it contains, of course, the totally positive. Okay, so I'll write it here parenthetically. Forgot it. They are the entry-wise positive matrices, square matrices. EP. Then we have the W non-negative matrices, which happen to be non-negative, but there's no other direct relation to anything, so I'll include them here. So W non-negative is a subset of entry-wise positive. And finally, another subclass of the semi-positive matrices, the one